We want to evaluate the limit of this polynomial here. And as I apply my limit laws, I can rewrite this as the limit as x approaches 3 of x squared minus 2 times the limit as x approaches 3 of x, okay, and then plus the limit as x approaches 3 of 4. Okay. And I'm going to write parentheses in here so we don't mix this up, of x and of 4. Okay. Now, there's actually one more thing I can even do to this that's a limit law, right? This 2 here I could put here instead. Okay. And the reason that I've done all this is, well, we actually know this limit here. The limit as x approaches 3 of just x is 3. Okay, so I have 3 squared. Okay. And I know this from the previous page. If we scoot back up, we'll see it. Here it is, when we're working with that identity function, right? The limit as x approaches a of x is just a. All right, so that step's taken care of. And then we have minus 2. And then once again, we have the limit as x approaches 3 of just x. So I'm going to have times 3. And then now we have the limit of a constant function. So the limit as x approaches 3 of 4 is just 4. So this turns out to be what? 9 minus 6 plus 4. So that is 7. Now, note, we could have gotten here just by plugging in x equals 3 into the polynomial. That's all we really did here. And we actually call this property here direct substitution. And we can actually do this to really functions that are nice. Okay, and we'll define nice a little bit in a little bit more detail later on. Okay, but for now, we know that we can at least do this to polynomial or rational functions. Okay, and so to finish this off here, if f is a polynomial or rational function and a is in the domain of f, then the limit as x approaches a of f of x is just equal to f of a. And again, right now this applies to polynomial and rational functions. And a rational function is just one that is a polynomial over a polynomial. Okay. I'll put an example here for you. And the fun there is short for function. Okay. So an example would be, say, g of x is equal to x squared plus 1 over 7x plus 3. Okay, right? The top part here is a polynomial, so is the bottom. So a polynomial over a polynomial is called a rational function. All right, so here we just have a little bit more practice with direct substitution. Okay, and everything in parts A, B, and C is technically either a polynomial or a rational expression. Okay, and again, direct substitution tells us that if we are working with a polynomial or rational expression, we just need to plug in really the x value. As x approaches -1, well, it should be the same as at -1. All right, and so what we get -5, and then we get a +1, -1, so this is just -5. Let's try another one. This one's actually just a constant function, right? Pi is just a constant, so this one's just pi. And then this one over here, we have a rational expression. We're just going to substitute in 3 for all the x's. We have 3 squared minus 6 times 3 plus 8, and then all over 3 squared minus 4. Okay. And so up top here, we have 9, then we have minus 18, and then plus 8, and then all over 9 minus 4, which is 5. So we're almost there. So we have minus 9 plus 8. So that's going to give us a -1 over 5. There we go. On to part D. Let's start trying to use direct substitution. And this is not the same example as part C, right? We're going as x approaches 2 this time, so just a little bit different. So we try and use direct substitution, but we have an issue. The denominator is 0. So we need to do something a little bit different. Let's see if maybe we can factor here. Okay. Those both look like they can be factored. So I'm looking for two numbers that add to -6 multiply to 4, multiply to 8. So that would be -4 and -2. So we have x minus 4, x minus 2. And then this is all over x plus 2 times x minus 2. And you might notice that these x minus 2's can cancel out. Okay, right? X minus 2 divided by x minus 2 is just 1, so we don't need to write those in there then. But the question is the limit of these two expressions really actually the same? Okay, or the limit of these two functions, even though they are technically slightly different. Let's see how their graphs do differ. We're going to do that down here. So let's maybe write in each function. So we have y equals, and what we had, x squared minus 6x plus 8 all over x squared minus 4. Let me make sure that that's right. Yeah, looks good. And then the other one we had was y equals x minus 4 all over x plus 2. Okay. And let's sketch in our axes. And I'm just going to look actually in one quadrant. I'm going to look in the fourth quadrant. Let me see if I can do a little bit better job there. Apparently not. Okay. So the important point here is at x equals 2, okay, now one of these doesn't have a hole at x equals 2 and the other one does. Okay, so the graph looks something like this around x equals 2, but the point is on either one of these graphs, if we come from the left or from the right, we're going to be approaching the same value. Okay, so what that means is I can use this x minus 4 over x plus 2 to find the limit I want. I can just use direct substitution on this thing. So if we do that, we get 2 minus 4 over 2 plus 2, which is minus 1/2. All right, so the next thing we're going to do is we're going to look at another one where the denominator is 0 and we can't use direct substitution. And here it is. Okay. Right? If I try to plug in h equals 0, the denominator is 0 and we have a problem. Okay. There's a little bit of a trick to these ones though. We can actually multiply by the conjugate. And so I oftentimes think about the conjugate whenever I see a square root plus or minus something, or something plus or minus a square root. Okay. So all the conjugate is it's the same expression, except for that sign in the very middle changes. So instead of minus 3, it's going to be plus 3. And again, this is called the conjugate, what we've multiplied the numerator and denominator by. Okay. And if we try to distribute here, we have the square root of 9 plus h times the square root of 9 plus h. That's just going to be 9 plus h. Okay. And then the middle terms will cancel. And then the last term, minus 3 times 3. So that's minus 9. And then this is all over. And we have h times the square root of 9 plus h plus 3. And we can go another step further. You can see that the 9's cancel. Right? 9 minus 9 is 0. So we get the limit as h approaches 0 of h all over the square root of 9 plus h plus 3. And I started to write this without the h in the denominator, and the reason for that is this h here is going to cancel, right? So this becomes the limit as h goes to 0 of 1 over the square root of 9 plus h plus 3. Okay. And you can see now if I plug in h equals 0, we don't get 0 in the denominator. We can actually do direct substitution now. Okay. A lot like in the last example. All right. And as h goes to 0, this becomes the square root of 9 plus 3. So this is just 1/6